Earth, our dynamic world, a planet teeming with life and activity, constantly evolving and transforming in ways both subtle and dramatic. Our planet is a dynamic place. It moves and breathes. It changes constantly. From the shifting of tectonic plates to the erosion of landscapes by wind and water, Earth is in a perpetual state of flux. We see evidence of this everywhere. The very ground beneath our feet tells a story of change and transformation, written over millions of years. Towering mountains pierce the sky, their peaks reaching towards the heavens. These majestic formations are the result of immense geological forces at work, pushing and pulling the Earth's crust. Deep ocean trenches hide beneath the waves, mysterious and largely unexplored. These underwater chasms are formed by the movement of tectonic plates, creating some of the deepest places on our planet. Volcanoes erupt with fiery power, spewing molten rock and ash into the atmosphere. These eruptions are a stark reminder of the intense energy and heat that lies beneath the Earth's surface. Earthquakes shake the very ground we stand on, causing destruction and reshaping the landscape. These sudden movements are a result of the Earth's tectonic plates grinding against each other. These dramatic events are not random. They are part of a larger, interconnected system driven by powerful geological forces. They are driven by a powerful force plate tectonics. This process involves the movement of large plates that make up the Earth's crust, constantly shifting and interacting. This process shapes Earth's surface over millions of years. Mountains rise, oceans open and close, and continents drift across the globe. Plate tectonics is a fundamental concept in geology. It provides a framework for understanding the dynamic nature of our planet. It helps us understand the history of our planet. By studying the movement of tectonic plates, geologists can reconstruct past landscapes and predict future changes. It also helps us understand other planets in our solar system. By comparing Earth's geological processes with those on other planets, we gain insights into the history and evolution of our entire solar system. Fossils embedded in rock layers tell tales of ancient life forms and environments, offering clues about the Earth's past climates and ecosystems. Satellite imagery reveals the ongoing changes in Earth's landscapes, from the melting of glaciers to the expansion of deserts, highlighting the impact of both natural processes and human activities. Scientists analyze geological samples in labs, using advanced technology to unlock the secrets of our planet's past and predict its future. Deep within the Earth, the core and mantle dynamics drive the movement of tectonic plates, creating a complex and ever-changing system that shapes our world. Despite the constant changes, diverse ecosystems thrive on Earth's surface, adapting to new conditions and evolving over time. People explore these natural wonders, gaining a deeper appreciation for the dynamic planet we call home. A global map shows the boundaries of tectonic plates, illustrating the vast and interconnected nature of Earth's geological processes. As the sun rises over a mountain range, we are reminded of the beauty and power of our dynamic world, a planet that is constantly changing and evolving. Plate tectonics, a planetary jigsaw puzzle. Imagine Earth's surface as a giant jigsaw puzzle. But this puzzle is always moving, constantly shifting and changing. The pieces of this puzzle are called tectonic plates. These plates are not stationary, they are in perpetual motion. They float on a layer of hot, molten rock called the mantle, which lies beneath the Earth's crust. The mantle's intense heat creates convection currents, much like boiling water in a pot. These currents slowly but surely move the plates around, causing them to drift. Where these plates collide, immense pressure builds up, causing mountains to rise and volcanoes to erupt. Conversely, where they pull apart, magma from the mantle rises to fill the gap, forming new crust. And where they slide past each other, the friction can cause earthquakes, shaking the ground above. This constant motion is responsible for shaping continents, creating oceans, and driving geological activity. It's a key reason why Earth is such a vibrant and ever-changing planet. Over millions of years, these movements have caused continents to drift apart and come together, forming supercontinents like Pangaea. Pangaea eventually broke apart, leading to the continents we recognize today. Oceanic ridges and trenches are also a result of tectonic activity, where plates diverge or converge. The Pacific Ring of Fire is a prime example of intense tectonic activity, with numerous volcanoes and frequent earthquakes. Tectonic plates even influence climate over geological timescales by altering ocean currents and atmospheric patterns. The distribution of fossils across different continents provides evidence of past plate movements. Human societies have had to adapt to the challenges and opportunities presented by tectonic activity. Innovations like earthquake-resistant buildings are a testament to our resilience and ingenuity. Scientists continue to study tectonic activity to predict future movements and mitigate natural disasters. The dynamic nature of Earth's surface is a reminder of the planet's incredible power and complexity. Understanding plate tectonics helps us appreciate the ever-changing geology of our planet. As we look to the future, the study of plate tectonics will remain crucial in understanding Earth's ongoing evolution. Indeed, Earth is a dynamic planet, constantly reshaping itself through the powerful forces of plate tectonics. This planetary jigsaw puzzle is a testament to the ever-changing and vibrant nature of our world. Mars, a planet of extremes. Mars is a planet of stark contrasts. It has towering volcanoes, vast plains, and deep canyons. But does it have plate tectonics like Earth? Mars is much smaller than Earth. This means it cooled down faster. A cooler interior might mean less active geology. But Mars still holds secrets. One prominent feature is Valles Marineris. This enormous canyon system dwarfs the Grand Canyon. It suggests massive tectonic activity in the past. The Red Planet's volcanic past, Mars, often referred to as the Red Planet, is home to some of the most fascinating geological features in our solar system. Among these, Olympus Mons stands out as a colossal giant. It is the largest volcano in our solar system, dwarfing any volcanic structure found on Earth. This behemoth, with its towering height and expansive base, suggests a history of intense and prolonged volcanic activity. The rugged terrain surrounding Olympus Mons tells a story of a planet that was once geologically active, with lava flows and eruptions shaping its surface over millions of years. On Earth, volcanoes are typically found along plate boundaries where tectonic plates either collide, pull apart, or slide past one another. These interactions create the conditions necessary for magma to reach the surface, resulting in volcanic eruptions. But Olympus Mons is different. Unlike Earth's volcanoes, which are often part of a chain or located along fault lines, Olympus Mons stands alone. Its unique features set it apart from any volcanic structure we know on our home planet. It sits on a vast volcanic plateau, far from any plate boundary. This plateau, known as the Tharsis region, is a hotspot of volcanic activity on Mars, home to several other large volcanoes. The geological features around Olympus Mons suggest that Mars may have experienced a different kind of tectonic activity compared to Earth. Instead of the shifting and colliding plates that drive Earth's volcanism, Mars's volcanic activity might have been driven by other forces. One theory is that plumes of hot rock, known as mantle plumes, rose from deep within Mars's mantle. These plumes could have created hotspots on the surface, fueling volcanic activity and giving rise to massive structures like Olympus Mons. These mantle plumes would have provided a continuous supply of magma, allowing volcanoes like Olympus Mons to grow to their enormous sizes over time. The lack of plate tectonics on Mars means that these hotspots remain stationary, allowing for prolonged volcanic activity in the same location. While Earth's plate tectonics create a dynamic and ever-changing surface, Mars's volcanic activity paints a different picture. The Red Planet's volcanic past, driven by mantle plumes rather than moving plates, offers a unique glimpse into the geological processes that can shape a planet. Understanding these differences helps scientists piece together the history of Mars and its potential for past habitability. Section 5. Venus, Earth's enigmatic twin. Venus is often called Earth's twin. It's similar in size and composition, but its surface is a scorching hellscape. Thick clouds trap heat, creating a runaway greenhouse effect. The surface of Venus is incredibly hot. It's hot enough to melt lead. This extreme heat has made it difficult to study Venus's geology in detail. However, we have learned some things. Venus has volcanoes, mountains, and vast plains. This suggests a history of geological activity. Section 6. Beneath Venus's veiled surface. Radar images have revealed intriguing features on Venus. There are signs of tectonic activity, but it's different from Earth. Instead of distinct plates, Venus may have a stagnant lid tectonics. In this scenario, the planet's crust is one solid piece. However, heat from the mantle still causes movement. This movement can create cracks, wrinkles, and volcanoes on the surface. This type of tectonics is different from Earth's, but it shows that geological activity can take many forms. Section 7. Icy moons, hidden oceans of possibility. When we think of tectonic activity, we often think of rocky planets. But icy moons can be geologically active too. Some moons in our solar system have a hidden secret: oceans of liquid water beneath their icy surfaces. These oceans are warmed by tidal forces from their host planets. These oceans could be home to life. but they also hold clues to the possibility of extraterrestrial plate tectonics. Section 8, Europa, Jupiter's icy enigma. Europa, a moon of Jupiter, is a prime example. Its icy surface is crisscrossed with cracks and ridges. These features suggest that the ice is moving. Scientists believe that Europa's icy shell may be broken into plates. These plates could be moving on top of the subsurface ocean. This movement could be driven by tidal forces from Jupiter. It could also be driven by convection currents in the ocean itself. If Europa does have plate tectonics, it would be a remarkable discovery. It would show that this process is not limited to rocky planets. Section 9. The search for extraterrestrial plate tectonics. The search for extraterrestrial plate tectonics is a challenge. We can't simply land on a planet and start digging. We have to rely on remote sensing and other techniques. Spacecraft have provided valuable data about the surfaces of other planets and moons. They've sent back images, radar data, and other measurements. Scientists are developing new technologies to study the interiors of other worlds. These technologies will help us understand what lies beneath the surface. Section 10. Unique tectonic features in our solar system. While Earth is the only known planet with classical plate tectonics, other celestial bodies exhibit unique tectonic features. Pluto, for instance, showcases a heart-shaped region called Sputnik Planitia, believed to be a nitrogen ice glacier. This region's formation and its potential impact on Pluto's geology are still being studied. Similarly, Saturn's moon Enceladus displays cryovolcanism, where water ice erupts from its interior instead of molten rock. This phenomenon points to internal heating and potential tectonic-like activities. Section 11. Conclusion. A universe of possibilities. So, do other planets have plate tectonics? The answer is complex. Earth is the only planet we know for sure that has the same kind of plate tectonics we see today, but other planets and moons show evidence of different kinds of tectonic activity. These discoveries tell us that our solar system is a diverse and dynamic place. As we continue to explore, we may find even more evidence of tectonic activity on other worlds. The search for extraterrestrial plate tectonics is a reminder that the universe is full of surprises.